How are you, students? This is chemistry for grade 9, unit 3, structure of the atom. Under this unit, today we are going to discuss on discovery of electrons. Students, after learning this topic, you are expected to explain the discovery of the electron, elicit the components of cathode ray tube, and you will be able to describe the properties of cathode rays. Before discussing on our today's topic, let us remember what we have learned in our last time lesson. The presence of positively charged particles in an atom has been predicted by Goldstein based on the electrical neutrality of an atom. That means, as we have discussed in our previous lesson, protons were earlier discovered as canal rays or anode rays by using anode ray tube. This anode ray tube contains perforated cathode through which the canal rays pass. So canal rays travel in a straight line and consists of positively charged particles. They deflect in magnetic and electric field. So bearing this in mind, let us discuss on our today's topic, discovery of the electron. Let us start from the Crookes discharge tube or cathode ray tube. William Crookes was the first scientist who designed the discharge tube, which was called the Crookes discharge tube or cathode ray tube. This discharge tube consists of a glass tube from which most of the air has been evacuated, having two metal plates sealed at both ends. That means the metal plates that attached or sealed to the positive terminal and the negative terminal, which are called electrodes. So these electrodes are connected to positive and negative terminal of battery. The electrode connected to the positive terminal is called anode, and the electrode connected to the negative terminal is called cathode. The electrodes are connected to high voltage, which is about 10 kilovolt to 20 kilovolt for the current to flow through the discharge tube. At high pressure, no electricity flows through the air in the discharge tube. So low pressure, that's about 0.001 millimeter of mercury, is used in that discharge tube. Now, when that much electric volt, that means 10 kilovolt up to 20 kilovolt electric volt is applied across the glass tube, he observed, or William Crookes observed, a greenish glow at the anode. So this is due to the fact that there are some rays traveling from cathode toward this anode, and when they strike the wall of the glass at the anode, greenish glow was observed. So the rays are emitted from the direction of the cathode and travel toward this anode. Hence he named them cathode rays. William Crookes named them cathode rays. J.J. Thomson performed some experiment on these cathode rays. In his experiment, he determined or he revealed some properties of these cathode rays. First, he tried to determine whether the cathode rays travel in a straight line or not. To do this, he placed an object on the path of the cathode rays, and then he observed that behind the cathode rays, there was a shadow of the object. They cast a shadow. So this implies that the cathode rays travel only in a straight line. So he concluded that these cathode rays travel only in a straight line. Second, he need to realize the particle nature of these cathode rays, whether the cathode rays are only rays or if they consist of particle nature. So in order to detect this property, he put some rotating wheel or paddle wheel on the path of the cathode rays. When the cathode rays strike the paddle wheel was rotating. So he said this implies that the cathode rays consists of particles, because only particles can cause the paddle wheel to rotate. The other point or the other property that he needs to detect is the magnetic and electrical charge or the electrical charge of these cathode rays. First, he needs to realize whether these cathode rays consists of charges or not. So he sealed two plates positive plate and the negative plate at either side of the cathode ray. Now, when the cathode rays travel, they deflected towards the positive plate. This shows that the cathode rays consists of negatively charged particles. Now, when magnetic field is applied perpendicular to the path of the cathode rays, they get deflected towards the north pole of the magnet, which is expected of negatively charged particles. This further confirms that the cathode rays are negatively charged. The first one is Thomson realized that the properties of cathode rays, such as charge to mass ratio, do not depend on the nature of the gas in the discharge tube or the material from which the cathode ray is formed. So, in order to detect this one, he changed the gas in the discharge tube and also the materials from which the cathode ray tube is formed. So, he observed similar properties for different materials and for different gases. So, he concluded that these cathode rays exist in all materials. Next, students, I want to invite you video which shows about this cathode rays discovery and their properties. Please watch this video.
Discovery. William Crookes discovered cathode rays when he was studying electrical discharge in gases, whereas J.J. Thomson discovered that the cathode ray consists of negatively charged particles called electrons. Production. Cathode rays are produced in a discharge tube. Hence, the discharge tube is generally referred to as the cathode ray tube. The cathode ray tube is a partially evacuated glass tube with cathode and anode placed at the ends of the tube. A vacuum pump is used to partially evacuate the tube. The cathode is connected to the power source with the help of a clip. The tube is supported on a stand. It was found that electric discharge through gases took place only when the pressure inside the tube is lowered and the potential difference between the electrodes was high. To produce cathode rays, high potential difference of 10 kV to 20 kV is applied between the electrodes and the pressure is reduced to 0.0001 millimeter of mercury by means of a vacuum pump. A glow is seen on the walls of the glass tube. The bright fluorescence glow is due to the striking of the rays emitted by the cathode. These rays are cathode rays. Properties of cathode rays. Cathode rays travel in straight lines. When an opaque object is placed in the path of the cathode rays, a shadow is cast on the glass wall opposite to the cathode. This shows that cathode rays travel in straight lines. Cathode rays consist of negatively charged particles. The rays deflect towards the positive plate when the tube is exposed to an electric field. This is because the negatively charged particles in the cathode rays get attracted towards the positive plate. Cathode rays are deflected by the magnetic field. When the tube is exposed to a magnetic field, the cathode rays follow a curved path, showing that they are deflected by the magnetic field. Cathode rays produce X-rays when they impinge on a metal with a high atomic weight. Cathode rays travel with a high speed almost equal to the speed of the light and hence possess kinetic energy. When cathode rays are made to fall on a paddle wheel, the wheel starts rotating, showing that the rays possess kinetic energy.
The other points that we have to discuss about discovery of electron is charge to mass ratio of an electron. After detecting the properties of cathode rays, J.J. Thomson also was able to calculate the charge to mass ratio of an electron to be 1.76 times 10 raised to 8 coulomb per gram, or 1.76 times 10 raised to 11 coulomb per kilogram. This can be determined by measuring the angle of deflection in magnetic and electric field. So I want to invite you a short video on this charge to mass ratio of an electron. Students, please watch the next video.
To understand how the charge to mass ratio of an electron was measured by J.J. Thomson. As you know, the atom is the smallest particle of matter, and electrons are subatomic particles present within an atom. How was the mass of an electron measured? Was an instrument used to measure it? Surprisingly, no. How then could scientists measure the mass of an electron? Let's find out. Charge to mass ratio of an electron. Once the electron was discovered, J.J. Thomson continued his efforts to calculate the charge to mass ratio of an electron through experiments. The experimental setup included a cathode ray tube. With a cathode, an anode and a metal plate. The anode he used in the experiment had a slit. At the end of the tube was a large sphere, coated with a phosphorescent material so that any beam after striking it would leave behind a mark on it. It was also provided with a scale to measure the deflection. At high voltage and low pressure, cathode rays were produced in the cathode ray tube. In the absence of electric and magnetic fields, the cathode rays produced were found to travel in a straight line without any deflection and struck the tube at point A. When an electric field was applied, the cathode rays were found to deviate from their straight-line path and hit the tube at point B. Similarly, when a magnetic field was applied, cathode rays were found to deviate from their normal path and strike the tube at point C. When both electric and magnetic fields were applied perpendicular to each other and to the path of the cathode rays, the rays showed deviation. Thomson observed that the amount of deviation of cathode rays depended on three main factors. 1. The magnitude of negative charge on the particle. The greater the negative charge, the greater was the deflection. 2. The mass of the particle. The lighter the particle, the greater was the deflection. 3. The strength of the electrical and magnetic field. The stronger the field, the higher was the deflection. Thomson calculated the charge to mass ratio of an electron by accurately measuring the deflection of electrons when varying strengths of electric and magnetic fields were applied. His efforts culminated in measuring the charge to mass ratio of an electron, which was found to be 1.758820 into 10 to the power of 11 coulomb per kg.
The other point that we have to discuss is about the discovery of charge of electron. As you can understand from the video, J.J. Thomson discovered the charge to mass ratio of electron to be 1.76 times 10 raised to 11 coulomb per kilogram, or 1.76 times 10 raised to 8 coulomb per gram. Now, How was the charge of electron determined? Another scientist named Robert Milkan determined the charge of an electron using an oil drop experiment. By using this oil drop experiment, he found the charge of an electron to be 1.60 times 10 raised to minus 19 coulomb. That means he used an instrument called atomizer. He sprayed the oil molecules into some material which is situated in a tube and which has a hole, small hole. Now the oil molecules attracted downward by gravitational force of the earth, and then he applied electric force or electrical energy that can attract the oil molecules that are negatively charged upward by comparing the gravitational force and the force of electric current or electric charge that he applied, determined the charge of electron to be 1.60 times 10 raised to minus 19 coulomb. So by combination these two discoveries, the mass of electron was calculated to be 9.11 times 10 raised to minus 31 kilogram. So students, now you are going to watch a video of this Robert Milkan's, in which he discovered the charge of electron by using oil drop experiment. I invite you to watch this video properly.
In 1906, Robert Millikan was able to determine the value of the charge on the electron in his oil drop experiment. A schematic of his experiment is shown here. It has an X-ray source placed over here and a high DC voltage source over here, capable of providing potential difference ranging up to 10,000 volts. Over here is an atomizer for spraying oil into tiny droplets, and a telescope over here to view the oil drop. Now let us see what we have inside this container. There are two plates over here. The oil is sprayed on the top like this. The top plate has a small hole over here. This hole allows the oil drop to enter this region between the two plates. The top plate is connected to the positive terminal of the battery. The X-ray comes from here and ionizes the gas that is present over here, which in turn charges the oil drop that enter in this region. Now at first the voltage is turned off between the plates. We watch the motion of the falling drop. First it accelerates because of the gravitational force Fg, and then due to viscous force Fv, a steady velocity is reached due to the air inside, which acts in a direction opposite to the motion of the oil drop. Let this velocity be v1. v1 can be known by recording the time required for an oil drop to fall a certain distance with a constant velocity. Let us see what forces act on the oil drop. While calculating the gravitational force, we have to take into consideration the buoyant force. Now Fg, which is the gravitational force, which is equal to 4/3 pi r cube rho minus rho air into g, where 4/3 pi r cube is the volume of the oil drop and g is the acceleration due to gravity. Rho is the density of oil and rho air is the density of air. Using Stokes' law, Fv equal to 6 pi eta r v1, where r equal to radius of oil drop and eta equal to viscosity of air. When the oil drop fall with constant velocity, then there should be no force acting on it. So these two forces are equal to each other. That is 4/3 pi r cube rho minus rho air into g equal to 6 pi eta r v1, or r square equal to 9 eta v1 divided by 2g rho minus rho air. Thus r is calculated if v1 is known, and accordingly fg can be calculated from this equation. Now the voltage is applied between the two plates. The top plate is connected to the positive terminal, and force due to electrical field, which is Fe equal to Q into E, on the oil drop act upwards, where Q is the charge on the oil drop and E is the magnitude of electrical field. This force can do two things. Number one, it may stop the motion of the oil drop. In that case, Fg equal to Fe equal to Q into E. Now E equal to V divided by D, where V is the voltage applied across the plates and D is the distance of separation between the plates. This implies Q equal to Fg into D divided by V. All the quantities over here are known, so Q can be calculated. Number 2. The oil drop may rise up with constant velocity V2, which may be experimentally calculated by recording the time required for the oil drop to rise a certain distance. Now the viscous force acts downward because the oil drop is moving up. Now since the oil drop is rising up with constant velocity, all the forces acting on the oil drop should balance each other. That is Fe equal to Fg plus Fv, where Fv equal to 6 pi eta r V2 and Fg is 6 pi eta r V1. Therefore, Q into V by D equal to 6 pi eta r V1 plus 6 pi eta r V2, which implies Q equal to 6 pi eta r V1 plus V2 into D divided by V. So in either case, Q can be calculated. The charge on different oil drops was calculated. Now Millikan prepared a chart like this. The chart showed the charges he got on the oil drops, and he found the difference between two charges like this. It was noted that the charge on an oil drop is always an integral multiple of a minimum charge, and the minimum charge was found to be 1.602 into 10 to the power minus 19 coulomb. Actually, the charge was considered to be due to electrons being attached to the oil drop. So this minimum charge difference between two oil drops was taken as the charge of an electron, which was found to be 1.602 into 10 to the power minus 19 coulomb. We already know the charge to mass ratio of an electron in the experiment of J.J. Thomson with cathode ray tube. The ratio was 1.76 into 10 to the power 11 coulombs per kg. From this, m equal to charge of an electron divided by charge to mass ratio, which is equal to 1.602 into 10 to the power minus 19 divided by 1.76 into 10 to the power 11, which is equal to 9.1 into 10 to the power minus 31 kg, which is the mass of an electron.
So from the video, an electron is the fundamental particle of an atom carrying a negative charge and having a very small mass. This small mass is about 9.11 times 10 raised to minus 31 kilogram. This mass of an electron is approximately about 1 over 1837 times the mass of hydrogen atom or mass of proton. That means 1837 electrons have a mass of 1 proton, which is equal to the mass of 1 proton. So let us do some exercise. I have about 2 questions. They are multiple choice questions. Number 1, which one of the following is correct about the evacuated glass tube experiment of cathode rays? A, very high pressure is needed in the tube to drive the cathode rays. B, very high electric current is needed to produce the cathode rays. C, the greenish glow is formed due to the interaction of the cathode rays with the glass tube at cathode. D, the air molecules in the tube have to be very dense to make the motion of the cathode rays successful. Which one of the following is correct? The second question, from his oil drop experiment, Robert Millikan was able to identify that A, the charge of electron to be 9.11 times 10 raised to minus 31 coulomb. B, the mass of electron to be 1.602 times 10 raised to minus 19 gram. C, the charge to mass ratio of an electron to be 1.76 times 10 raised to 8 coulomb per gram. D is the charge of electron to be 1.602 times 10 raised to minus 19 coulomb. Let us see. The first question says, which one of the following is correct about the evacuated glass tube experiment of cathode rays? 1. Very high pressure is needed in the tube to drive the cathode rays. This is completely incorrect because very small amount of pressure, that's about 0.001 millimeter of mercury is needed, because if there is high pressure, the electric current cannot flow and cannot form cathode rays. B. Very high electric current is needed to produce the cathode rays. This is true because about 10 kilovolt up to 20 kilovolt power is applied across the cathode ray tube. See, the greenish glow is formed due to the interaction of the cathode ray with the glass tube at cathode. Actually, a greenish glow was observed by the interaction of the cathode rays with glass tube, but it is not at cathode, it is at anode, because the cathode rays travel from cathode to anode. At anode, when they strike with the wall of the glass, a greenish glow was observed. These air molecules in the tube have to be very dense to make the motion of cathode rays successful. This is completely incorrect because it is a partially evacuated. That means a small amount of gas molecules exists there. So the correct answer is B. Second, from his oil drop experiment, Robert Millikan was able to identify that the charge of electron to be 9.11 times 10 raised to minus 31 coulomb. Actually, he determined the charge of electron, but the value was not this one. This is the mass of electron, not in coulomb, but it is in kilogram. The mass of electron to be 1.602 times 10 raised to minus 19 gram. This was 1.602 times 10 raised to minus 19. It is not a gram, or it is not a mass, but it is a charge. The charge to mass ratio of an electron to be 1.76 times 10 raised to 8 coulomb per kilogram. This was determined not by Robert Millikan, but by J.J. Thomson. The charge of electron to be 1.602 times 10 raised to minus 19 coulomb. D is the correct answer. Good. Students, let us summarize what we have learned in our today's lesson. In our today's lesson, we have discussed about the discovery of electron. The discovery of electron was begun by the discovery of cathode rays, which are later called electrons. William Crook discovered cathode rays by using partially evacuated glass tube called cathode ray tube. Later, J.J. Thomson studied the properties of these cathode rays by performing different experiments. From his experiment, he determined that the cathode rays travel only in a straight line. They possess mass or kinetic energy, and also they have negative charge, or they are negatively charged particles. And finally, they exist in all materials. So from his experiment, he realized the cathode rays have these properties. So students, this is all what we have for today. Next time, we will join with some other topic. Till then, goodbye.